Welcome, I'm John Titus for EE Times Innovation Generation. In this video segment, I'll describe how we can use small transistors like this one to drive LEDs, turn them on and turn them off. You might ask, well, why do I need a transistor? I can just supply some current to the light emitting diode and turn it on and take the current away and turn it off. Well, transistors can take a small amount of current and turn it into a large amount of current. It doesn't actually create that current, it just switches that current on and off through the transistor. So a little bit of current going into the transistor or coming out of the transistor can control a much larger amount of current flowing through the transistor and thus your LED. So let's take a look at the two types of transistors that you can use to typically drive LEDs. I'll draw the symbol for the first one and then the second one. The first one uses a circular symbol with two lines that come in. One has an arrowhead and comes out like that. This arrowhead is called the emitter, and we'll give that E. The line that comes off at an angle is called the collector, and we also have a base. This is called a PNP transistor, PNP, and we have a complementary type transistor to that. It has the same elements, but drawn and arranged slightly different. Here's a collector, an emitter, and a base. And this is called an NPN. And as you'll see, there are uses for each of these types of transistors when we get into driving LEDs. It's important to note from the arrow how current flows through a transistor. And you can use the arrow. Current coming in on the arrow gets split between the collector and a small amount coming out the base. In an NPN transistor, we have current going out the emitter and coming in on the collector and also coming in on the base. So the emitter current is the sum of the collector and the base current. Here, the emitter current is the sum of the base and the collector current. We supply a small amount of base current or draw a small amount of base current, and that controls a large flow from emitter to collector in the PNP or from collector to emitter in the NPN. Well, how do we figure out how much control we need on the base to give us a sufficient current flow for LEDs? Well, you need to look in a data sheet for the transistor that you're using. In this case, we'll use a 2N3906 as our PNP and a 2N3904 as the NPN. So I looked in the data sheet, and this has a DC current gain of 60 for a current of about 50 milliamps. So let's assume that we've got something that's going to take 30 milliamps, and we can assume then that the gain is about 60. Typically in a data sheet for a transistor, you'll see the gain specified either of two ways. One is H with a lowercase fe subscript. That's also equal to the Greek B or beta, which stands for gain in some data sheets. I think HFE is still probably more common in data sheets. In this case, that equals 60. So that's the gain. That means that if we put 1 milliamp in here, we can control the flow of 60 milliamps through the collector to emitter within the transistor. So let's set up a little circuit and see exactly how this can work. I'll draw a PNP transistor to start. And we'll go through a current limiting resistor to a light emitting diode, and then we'll go to ground or 0 volts. And here we'll say we have plus 5 volts going into the transistor, and here on the base we're going to draw a certain amount of current out, and we want to limit that amount of current, so we'll have a resistor there that also goes down to ground. And it's the value of this resistor that sets the current flow from the base to ground. So we want to set this so that it's going to be a 1 to 60 current ratio. So if we have, let's say we have 30 milliamps over here, and we have a gain of 60, that means we need a half a milliamp over here. But because we're going to use these transistors as switches, we want to make sure that we drive them hard. That means we probably supply or draw a little bit more current than is necessary. So let's say it's twofold. So instead of having a half a milliamp, we'll draw 1 milliamp. So we want a flow here of 1 milliamp. Well, how do we figure out what the resistor should be? If you use a meter, you'll find that there's a voltage drop between these points of about 0.7 volts. So at this point then, with respect to ground, you have a voltage of 4.3 volts. So I equals E over R. And we want to find R, so we can rearrange this and say R equals E over I. And we have E as 4.3 volts, and I, again, we have to express I in units of amperes, not in units of milliamperes. So here we have 0.001 amperes, and if we divide this, let's take a calculator and just do it. You can probably do it in your head, but we'll just do it for fun. 4.3 divided by 0.001, that equals a resistor that has a value of 4,300 ohms. So let's get rid of some of this clutter. If you set up this circuit and you have a resistor here that's 4,300 ohms, and you have this transistor, which is a 2N3906, you can send 30 milliamps down through this light-emitting diode. And the resistor here, you have to calculate the value for the 30 milliamps. Just remember that you've got a certain voltage across the light-emitting diode, and you've got also about 0.7 volts across the transistor. So that leaves you the voltage across the resistor, which you can use in Ohm's law, knowing that you've got that voltage as well as the current, and you can figure out a resistor value. So again, to review, you need to know the beta for the transistor you're using to determine how much current. In this case, from a PNP transistor, you're drawing from the base down to ground because that current's coming in through the collector, through the emitter, and then down through to ground. So that's what the beta gives you. You can use Ohm's law to figure out exactly what value of resistor to use in this circuit. Now let's just make sure people understand that if you take that resistor out and no current can flow, the transistor turns off. It's only when we have a potential out here that allows us to draw current down to ground that transistor is going to turn on. Let's take a look at another example that uses an NPN transistor. You'll see the circuit changes, but the calculations are very much the same. We'll start with a 5-volt potential come through a resistor to a light-emitting diode down to our transistor, and then to ground. And then we need a base resistor here. Now you remember from earlier that in this case current is coming in this way, current is coming in this way, and it's going out that way. Again, we've got 30 milliamperes here. We have a 2N3904 transistor that has an HFE equal to 60, or a beta equal to 60. So the calculations are similar, Again, you want only 30 milliamps flowing through the light-emitting diode. And it doesn't matter whether the resistor is first or the LED is first. You can switch those as long as they're in series. Now, in this case, what we need to do is supply current. So if we have some kind of logic device out here, we have to know that, in this case, again, we want 1 milliamp because our beta is exactly the same. So we want 1 milliamp here to control 30 milliamps out there. If you use beta, it's only half a milliamp, but we want to drive it hard to make sure it fully turns on and we get all that current going through the transistor. So we're using 1 milliamp here. You can use a little bit more current if you still want to be on the safe side. But here, in this case, you might have plus 2.7 volts out of a logic device. So your voltage is somewhat different. You've got across here, you've got your 0.7 volts. So here you've got 4 volts across the resistor. Again, I equals E over R. We want R, which is E over I. So we have R equal E. The potential here is 2.7 minus 0.7, which is 2.0 volts. And in this case, we've got 1 milliamp here, or 0.001. And again, you can probably figure out exactly what that has to be. We'll do it on the calculator again. We'll say 2 divided by 0.001. It's about a 2,000 ohm resistor. So you've got a basic circuit here that you're supplying current at 1 milliamp into the base of this NPN transistor, which is a 2N3904. When you do that, it allows current to flow from the 5 volt supply through the resistor and the LED, through the transistor and ground. And you've essentially amplified current. You've taken 1 milliamp in, and for that 1 milliamp, you've been able to control 30 milliamps through the LED. So that's the basics of using transistors to drive LEDs. Find the data sheet for the transistors you want to use. Find the data sheet for the LEDs so you know how much current it will take, and you'll be in good shape.